Okay, welcome again to this third session, or third talk, who is going to be given by Christoph Sorger, he's the director of the Institute, National Institute for Mathematical Sciences and its applications, or interactions from the CNRS. Welcome.
Well, thank you very much for being here in this pleasant place. You're correct, Alejandro. The UMI in Chile was the first one. So it was the first international mixed unit that the CNRS created. So this is not that known, but still quite well known, at least at our place. Maybe also one could add that a small part of, maybe a third of the international mixed units are mathematicians. So it's very natural for us, a little bit more than the other disciplines. What is less known is that even the first mixed unit at all in France was also a mathematics institution. So it was the Institut Mathématique de Recherche Avancée à Strasbourg. So it has been created in 1966. So I think we mathematicians, we are just good at creating new structures. And this is certainly my understanding, is why it is always the mathematicians who start with these things. So I'd like to talk about, so the title was Singular Symplectic, Complex Symplectic Manifolds. I would like to start with some classical examples. What I would stress on is more on singular symplectic hypersurfaces. So one disclaimer in the beginning, so whenever I'm talking about symplectic, it's not the same symplectic, at least not the same symplectic as we heard in Emmanuel's talk. I'm always talking about holomorphic symplectic structures. So I will explain this, but the word of holomorphic symplectic geometry is different from the world in symplectic geometry as we've seen it this morning, but there are many similitudes, and there are many ideas you can take from classical symplectic manifolds, and maybe we can see something working here today. So let's have some fun and start with a very classical example. So I'm looking at 2x2 matrices with determinant 1, and inside there a finite subgroup. Let's suppose it's a non-trivial finite subgroup. So F will act on C2, and I can divide by F, and I will get a surface. And this surface, let me denote it by XF, and it's singular at exactly one point, the point when there's a non-trivial stabilizer, and this is at the origin. So it's a surface which is singular at the origin. And so when you look at these surfaces, so how does an algebraic geometer understand those? He would look first of all at the ring of affine functions on it. So if I look at x of f, so this is just functions in two variables which are invariant under the induced action of f under the ring of functions over C2. So this is just polynomials in two variables. So let us look at a small example. So maybe the easiest one for such a subgroup. We write it over here. So let's look at the cyclic group of order n. So it's just matrices of the type psi f minus 1 generated by those where psi is a primitive nth root of unity. So for n equal to 2, you just get plus or minus 1. And so if you look at the action over here, so if you look at the function, so it will just act on the first by multiplication with psi, and on the second by multiplication with psi minus 1. So what are typical invariant functions we are seeing here. So we are looking at invariant functions. So of course we have u to the power of n, and we have v to the power of n. And of course if we take u times v, so the action is psi times psi minus 1, the psi will still disappear. So u times v is another invariant function there. So it's easy to guess. So let me call this variable x u up to n, y v up to n, and z u times v. So then what we see is that they have an equation that zn up to n is equal to x times y. And it turns out that this ring is nothing else. It's c of x, y, and z divided by the relation. So we get embedding of xf inside C3, and it's just given as a zero locus or the vanishing locus of this function f, which is written there. So, of course, you know these things very well. It's interesting to look at that. First question, which is a very old question, is going back to Duval and Klein, is what are the possible xf's we can have. Of course, this is easy to answer once we ask the questions like that. It's not the way how they looked at that. We just have to classify finite subgroups inside SL2 of C. So how do we do that? Of course, we can always conjugate our finite subgroup. So it will be we can suppose it's a subgroup of the special unitary group 2 by 2 matrices. And then we know that this is nothing else than the unity sphere inside the quaternions. And then we have a natural projection to the rotations in SO3 of R. So this is just the unit sphere inside the quaternions. And so a quaternion, you can write it as a so you have the norm, just take the squares. And then there's a natural way to associate to A, B, C, and D a matrix which will define the isomorphism. And what is the action? So here inside we have an R3, which is just first coordinate trivial. And then the action is just, if I have a Q, at X, I send it to X, QX, Q minus 1 are just composed. So this is an element of SO3 of R. It's easy to see that this is surjective. So I get plus minus 1 as the kernel. So if I have a finite subgroup here, it will give a finite subgroup inside SO3 of R. And those finite subgroups we learned it in school, maybe not in school, but at least at the beginning. So these are just some cyclic groups, some diagonal groups, and then there are the symmetries, several symmetries could let me just for the tetrahedra, of the octahedra, and of the isochahedra. And so if we go back to those, we can get the list. We can get the list of possible subgroups. So we have the cyclic group. We have, which I will just write like this. So of course, we always must be careful. We have to pull them back, so it will get multiplied by 2. So let me write it like this, dn minus 2. And then there is this one, let's just call it T, O, and I. Cardinality here is 120. And then we have 48, 24. This one is 4n minus 2. And this time is, of course, n plus 1. So then the exercise is to translate this into equations. I will not do this for all of them. I already wrote the one here. Let me just write the last one. So this is x power 2, y power 3, plus z power 5. And it turns out we are always, in this case, 3 invariants, 1 relation. And the equations here are very well known, because these are the equations for ADE singularities. So why do we call this ADE singularities? This is probably the fact how they were introduced first. So if you look at the minimal resolution of XF, resolution of singularities. So we just have to look what happens over the singular point, and it's a tree of P1s. And it turns out that you get so you have a graph. So the nodes are the components, and you have an edge if the intersections of 2 components is non-trivial. And the graphs you get here is the Dynkin graph for A1. Here the Dynkin graph for Dn. And these are the graphs for E6, E7, and E8. So somehow one might say that now the whole thing is over, because this thing is very classical, has been introduced from many points of view. But I would like to think about how can we generalize these equations here to higher dimensions. So what is a good generalization of this picture, maybe to 5-dimensional space, 7-dimensional space, and what is a good way of thinking of this? Of course, you never know what is a good way of thinking of this unless you have started to think about something. So we'll show you something, and maybe it's not the good way of thinking at it, but at least give some ideas. So I want to show you some singularities. So the most classical one is the A1 singularity. So you just divide. I'm turning it around. But we can also have a look at. Let's look at D4. If the internet would like to do it. Okay, so doesn't want to. So, but you can go on my homepage. Come slowly, and you can look at the pictures. What is interesting is, so this looks like a trumpet in 3 parts.
It's slow.
It's just slow because it's in French, so we need to.
Translate. I think if you wait for it.
I think it's okay. We see it already here. We see the singularity here. Just let me deform it, because whatever one likes to do in algebraic geometry is once you have an object, the object by itself is not interesting. What is interesting is the deformation of its object. So here you see the deformation. So it's just the cone, but it gets thickened up at the origin. And you see A1 here, it's just the circle here. So it's more interesting if I take A3, just in order to show you a deformed A3 singularity. So this is, you see it actually here. This is a formed A2 singularity, so it's a saddle. So here it's A3. Singularity comes on. And when you see how it deforms, you will see 3 circles which arrive, which are connected by 2, which will just intersect each other at the middle of those. So you just see the A3 diagram, and in the same way you see the D4 diagram. So it's somewhat interesting to see it once completely. So maybe oh, sorry, let's just continue. Just to see it arriving here. Okay, so maybe now I need your help for the...
Más diagonal.
Wow. Bravo. So I close this. Okay, so what do I understand by so let why I will call it a symplectic. Start with y, an algebraic or complex smooth variety. So what a holomorphic form, so it's just a section, a holomorphic 2 form. Here inside is, for me, is a symplectic structure. So holomorphic, huh? Symplectic structure. If it is closed and non-degenerate. So this is very easy definition. Just copy the classical definition and just use the holomorphic context. I would like to think about singular symplectic varieties, because these are the ones I would like to introduce. So let's suppose y is only normal. So a normal variety. So maybe singular. So I have a regular part. So this I will call a symplectic variety. If the regular part admits a symplectic structure, and if, so let me call this sigma reg, and if I look at for every resolution of singularities, if I pull back this, so this will live on so if this section extends to the whole, so it extends.
It's non-singular.
No, this is the basic point. You don't ask that the extension is symplectic by itself.
Could be degenerate.
It could be degenerate. So it's not that strong what we ask for. But this is the right definition. This definition is due to Bouville, and it's a very inspiring definition in this context. Whenever it extends to a symplectic structure, then we call this resolution a symplectic resolution. But let's not go into this detail here. So coming back to our example, so it turns out that V of f inside C3 is an ADE singularity. Actually, precisely when F is a symplectic hypersurface. So this translates the definition of ED singularity just in another way. It just means you have a form. You see it here. The form sigma is given by the residue of dx divided by f. So if you pull it back and you do the computations, you'll see it extends. And actually, it extends even symplectically. But let's so basic question. Yeah.
What about other singularities, symplectic that don't embed in C3? Is there some?
Yeah, I'll talk about that. That's the basic question. You're faster than I can talk. Can we find? So let's take some f in some in say 2n plus 1 variables. Let's suppose it's quasi-homogeneous just in order to avoid some trivial cases, and look at v of f inside 2n plus 1. So what are the equations? Symplectic. What are the equations we can find? Classify them. So my first guess, so it's common work with Manfred Lehn, was this implies necessarily n equal to 1, and we are in the ADE case. And we tried very hard to prove it. And you know a good theorem is invariant under deformation of its proof. And the bad assertion, whenever you deform the proof, it will never get correct. So it's exactly what happened to us. So we were unable to prove this. So we tried to find examples, and we found some. So for n equal to 2, we write down the equation, a square x plus 2ab xy. Must be careful that no y only, plus b square z. So this lives in C, x, y, z, a, and b. So this gives a series. And let me say this is related to the series CL, Cn. And we know about one other case, so one complicated equation in C7, which is related to the Lie algebra G2 or the Lie group G2, and we don't know about no other equation like that. So please find out, try to give me a new example. And it turns out what happens is that this symplectic condition is very strict. We've already seen it when we were trying to classify compact hyperkähler manifolds. So I worked a lot on this subject. So you have your Hilbert schemes, and you have moduli of some moduli spaces of sheaves over K3 surface. And so there's a finite list of examples. And here's a little bit the same. So the fact you ask two things which are a little bit contrary to each other. You asked it to be symplectic, but you also ask it to embed in a very low dimension. Of course, if you allow yourself to embed in high dimension, you have many examples which you can construct, but you don't allow it to embed in a high dimension. So let me show you how we found these examples. Of course, we didn't use a computer, or you can't find these examples without thinking on something else. So as I told you already, the good way of looking at it is at deformations. And so what does it mean to deform a symplectic variety? So you have X and you have your form, but symplectic structures don't deform. This doesn't make any sense. What makes sense for them is to look at resolutions of singularity. But whenever you have a symplectic structure on a normal variety, of course you have a Poisson structure defined by the symplectic structure, at least on the regular part. So we have a Poisson structure. It's defined the same way, in the classical way, on the regular part. So this is, you have two functions, f and g, and you have a Poisson bracket to get a new function. But these are functions on a normal variety. So the bracket extends to whole x. So the Poisson structure makes sense on the whole variety, and this is why we have put normality into the game in the definition of symplectic varieties. So this extends to the whole x. So if you really would like to understand these things very well, one has to look at Poisson deformations of x and try to understand what are the possible Poisson deformations you can find once you have a symplectic hypersurface in some affine space. And so there's the idea of how to do this is already known in the case for two variables. So in the classical case of ADE singularity, and it's due to Grothendieck in his ICM talk in Nice in the 70s. So he's told us to look at the Lie algebra G, and it can always send it. You have always an adjoint action of the group, the joint group on G, and then you can send it to the quotient. This is just a semi-simplification of a matrix. We all know when the Lie algebra G is just the trace-free matrices. And then, of course, we know also that if you take the invariance of G under the adjoint action, this is the same thing as to look at the Cartan subalgebra and to look at the invariance under the finite group, the Weil group. So we have a natural map to H mod V. Everybody knows this map for SLN. So here we go to Cn minus 1. So if you have a matrix, so we just take the characteristic coefficients of the characteristic polynomial. So this is a very classical map. Here inside, we have the null, and over it we have the nilpotent orbit. And it turns out, if you look at G cross small b, so there's a natural map from this. So this is a Borel group, and the Borel Lie algebra, you just can take the product and take the adjoint action, you will enter up in G. Let me just forget about the precise definition, but think about it with a twiddle over it, and then you have a natural map here inside, and the diagram which Grothendieck has told us is just to say, look over here, and then we have here also so we have an n tilde here, and so this is at least he understands it as a simultaneous resolution of singularities. And what Grothendieck did was to show that at least in the case for nilpotent orbits, which are, so here we have the nilpotent cone, and every cone has an orbit. So if you take a nilpotent element, x, so you look under its orbit, under the action of the adjoint group, and you take a nilpotent element here inside. So whenever you have an x, you can find a y and an h such this is an SL2 triple. And what you can do is to define a slice to this orbit, let's call it S. And so when you look at this slice, you can look at the intersection of the slice together with n. So this, let me call this S0. And now it's very interesting to study this object here, the intersection of the slice together with the nilpotent orbit. So it turns out, I'm going fast because time is running out, that S0 is a symplectic variety. And secondly, the map, here I have the slice. So I can take, here was my intersection. I can do the same here. So I will get S tilde and S0 tilde. And S0 tilde to S0 is the formal universal Poisson deformation, except if, and there are a list of cases I will not write down, but which is precise. So this is a theorem which is due to my colleagues Manfred Lehn and Namikawa and myself. And it turns out that, of course, it's very well known in the special case when you are not in the minimal orbit, but when they're in the subregular orbit. And there it has been proved in this special case of the subregular orbit by Briscoe and Slodovich. So what we did was just to understand their work on the subregular orbit for all orbits, for all nilpotent orbits. They couldn't do it at that time because they didn't have the notion of symplectic variety. But if you look in the case of the subregular orbit, so the subregular orbit is the biggest orbit, which is not the whole. So this is of codimension 2 inside n, the subregular orbit. So if in this case, S0 is a surface, and whenever G is ADE, we get back our XF of the beginning. So when G is not ADE, we are in the exceptions case. So there's a list of exceptions for the other groups. And this list of exceptions just tells us that it's not the universal. In this case, it's a semi-universal minimal resolution for them. And in that case, it's not the case. So you can factor out, and you will come back to the initial ADE singularities. So the examples I've shown you are the examples where precisely we are in the case when S0 is a hypersurface. So we looked at all the cases you can find. You know all the nilpotent orbits, so you can look at them. And then you see, so in the cases of CL inside for C5 and G2 for C7, S0 is a hypersurface. And this is good cases because they are not in the exceptions. Okay, so I'll stop here, and thank you very much for your attention.
Are there any questions, comments?
Is there an analogy like the Klein singularities? There are finite groups acting on these examples that I mentioned in 5 variables. There are finite groups, are quotients of, are orbitals?
No, we asked ourselves these questions and we didn't find them. So maybe.
Because we're natural, not to.
Of course, we would like to have the same description.
Client definition.
But
Comment?
you might think about orbifold structures or something like that. But we didn't see this. So probably that's not the case.
If you have a hypersurface in C7, the link has to be simply connected. So the construction cannot be just the same.
No, there must be different.
Okay, any more? Oh, you think I get the speaker?
Okay.
Sorry.
No, thank you. So I just invited you. Please find new examples. It's very concrete. So, okay, thank you.
Thank you.